Hi, my name is Eddie, and this is my Chapter 14 portfolio. The technical definition of the partial derivative are that they are applied to functions of more than one independent variable with respect to one variable. Likewise, like a normal derivative, partial derivatives also convey a rate of change in a certain direction. Partial derivatives differ from normal derivatives in that the normal derivative is given by the equation fa plus h minus f of a over h, whereas the partial derivative with respect to x is given by fx a comma b with the limit of h approaching 0. Likewise, it uses the same function as the normal derivative. The only difference is that there's a comma b in front of them next to the a. And with respect to y, it's given by the same thing. The only difference is that there's a plus, the plus h moves to the other side where the bu should be. Likewise, a good example of a partial derivative is the graph shown below, in which you can see that the planes are going in their own directions, but they also share a point. Next, so this problem conveys how different quotients convey different results. Because they're being solved with respect to different independent variables, x and y, this problem asks to use the different quotients that I alluded to in the last slide to find the partial derivatives at the points 3, 2. As you can see, they both yield different results, which is the main idea to keep in mind for partial derivatives. I would like to mention that the main theme of this chapter is the use of partial derivatives. Partial derivatives are very common in the real world as they are in this chapter. Partial derivatives are used in basic laws of physics, for example, Newton's law of linear motion, Maxwell's equation of electromagnetism, and Einstein's equation of general relativity. So back to the problem, equation 20 is interesting in that it shows that you can use data analysis with partial derivatives. So for example, f with respect to x of -2 comma -1 yields positive numbers while looking at the graph. And the same could be said for a, b, and c, in which that with the respective values in which you're going for and respective partial derivative. So for x or y, you're able to tell, for example, for b it's negative, c it's positive, and d is also positive just by looking at the table. So next, local linearity in differentials. Local linearity is the idea of zooming into a point sufficiently so that a non-linear function that is differential will look linear. This can help approximate for values and construct a tangent line. A good example of this is the function of x squared, as you can see by the graph, at which it doesn't look linear at all. But if you zoom into the curvature, you can see that in fact, as you get closer to the line, it starts to look linear. That is the idea of local linearity. But what about differentials? Well, differentials, don't know. Sorry about that. Well, differentials represent a change in the value of the function as we move from a point A to a nearby point x comma y. Next, for this problem, you are asked to find a local linearization at the function x squared y at the point 3 comma 1. So you take the partial derivative with respect to x and y and plug in the points that you are given, which are 3 comma 1. And when you plug in your information into the linearization formula for the 2 dimensions, you get z equals 9 plus 6x minus 3 plus 9 parentheses y minus 1. Likewise, the main takeaway from this is that your answer is a linear function rather than a function with curves. Here you're asked to solve for the differential at the given point. So similar to local linearity, you take the partial derivative, add them, then set them to the variables to the given values, and you get the answer for dx. So for directional derivative, the directional derivative tells us intuitively that if you have some multivariable function of f x comma y and a vector in the function's input space v, the directional derivative of f along v tells you the rate at which f will change while the input moves with the velocity vector v. The idea being that the gradient vf is computed by taking the dot product between the gradient of f and the vector in which the gradient f dot product is v. Which means that it makes sense that the directional derivative comes from the dot product of the gradient and the direction unit and the unit vector because they are all used in relation to one another. Likewise, the directional derivative can be used without the dot product, in which v would not equal 0. However, the use of the dot product is considered a shortcut to figuring out the direction of the derivative. So the two ways of thinking of the directional derivative is one with the dot product and one without it. Moreover, the main idea here being that they both describe direction. As noted in the graph, v is the vector in which the dots leading up towards the gradient is how one is able to solve for what direction the points in between the y are. Likewise, it's good to note that the vector only represents a small portion of the gradient, and not all of it, because as we know, there are limited ways to describe a gradient by different points or vectors. For this problem, we are asked to use or to find the directional derivative in which the vector is defined. We first need to find the partial derivative of the function. Then when we set the partials to 1, 2, you are able to find the vector of f, which is replacing the x and the y with I and j. You then multiply the new vector by the u vector to get the value of -46/5. The important idea here is that the directional derivative must be a number and it can't be a vector. For this problem, you again start with finding the partial derivatives and setting them to the points provided. Then also you must find the magnitude of the u vector. Then you do the dot product of the new vector you found to the one provided at the start. Again, your answer is a number and not a vector. The main takeaway is that directional derivatives will always be a number. So the most important thing to remember about the gradient is that the gradient of f is evaluated at an input, so that, for example, x naught and y naught will be a point in the direction of steepest ascent. Each component of the gradient tells you how fast your function is changing with respect to the standard basis, which is why the gradient points of the direction of greatest increase or ascent of f. Moreover, the magnitude of the gradient vector will give you the rate of greatest increase of f because they are going in the same direction. An example of this is when you're asked to find the gradient of the greatest descent, you put a negative sign in front of the magnitude of the gradient vector. Also, gradients are perpendicular to level curves or surfaces of f because gradients are orthogonal to level curves and level surfaces, meaning they are perpendicular or form right angles. The y to this, or answer, is that by the proof of every curve, the directional vector of rt on the level curve or level surface satisfies d over dt f r of t, which equals 0. And by the chain rule, the gradient of f directional vector of rt is perpendicular to the tangent vector of r prime of t, or r derivative of t. Lastly, the equation of the tangent plane is given by the bottom equation under the graph because as I alluded to before, each component of the gradient tells you how fast your function is changing with respect to the standard basis. So if you look at the tangent plane equation, you can clearly see that it's made up of 3 parts: the partial derivatives of x and y, and by the points of the z function, z minus f a comma b equals 0. Here's a quick example in that snowboarders keep gradients in mind when traversing down a snowy hill. They are looking and predicting in the case of the gradient of greatest descent rather than ascent because, well, they're going down. For this example, you can see that you start first by getting the partial derivatives of the function. Then while adding them together, you solve for the points given. So 2, 3, and your gradient of f at 2, 3 would be a vector, not like the directional derivative with it, which is a number. Like the last example, you can see that you need to start with the partial derivatives, then add the new 2 partials together and solve for the points -1, 3, and the gradient of f, which would be 1 over 100 2i minus 6. So the chain rule states that the derivative f of g of x is f prime of gx times g prime of x, in which the chain rule helps composite functions like sine x squared. So the chain rule plays a very key role in solving or compositing functions that would be a nightmare to solve without it. Not only is the chain rule a quick way or shortcut to solve, it's the most important rule of differentiation. Note on the side note, the chain rule was used heavily by Isaac Newton, so that shows how important it was. There's a graphic here that shows the chain rule, how the chain rule is conveyed visually, which you can see how it works because of the various sporadic lines, which are composites of f and x. Here's a basic example of the chain rule, in which you take the chain rule of z, x, and y and add them after. You can see from the chain rule formula that it's a very straightforward process, which does not take too much time. In this problem, you can see other implementations of the chain rule. Here we need to solve for the Coulomb production. First we find delta R and delta T and use the equation that was provided of delta C to solve for dC over dt. With the given new points, you get negative 0.6. This problem conveys that the chain rule can really be used for numerous amounts of problems, from complex equations to solving for Coulomb production. The chain rule is really an important part of solving problems. The second partial derivative of the partial derivative of the partial Sorry, let's write that again. The second partial derivative is the partial derivative of the partial derivative, in which fx of x would mean that you will be taking the partial derivative of the function with respect to x twice. Likewise, the unmixed partial derivatives fx of x or fyy tell us about the concavity of the traces, or the lines. It's a fancy word. Likewise, the mixed partial derivatives fx of y and fy of x tell us where the graph of f twists. A good example of this is the graph shown, in which you can see where the unmixed and mixed derivatives are. Moreover, an important idea that helps with the second partial derivatives is finding if f has a local max, local min, or if it's undetermined, which is found through the help of the Taylor polynomial, or known as the quadratic approximation, in which the theorems are listed with how you can tell if it is a max, min, or if it's undetermined. However, mixed partial derivatives fx or fy of x are not always symmetrical. Technically, the symmetry of second derivatives is not always true. There's a theorem referred to as Schwarz theorem or Clair's theorem, in which states that the symmetry of the second derivative will always hold at a point if the second partial derivative are continuous at that point. And that example that really, and that's an example that really doesn't show that they're always, it doesn't show that it's true at all places because of the piecewise function. This is the only exception that I was able to find that actually proves that not all of them, it's like not safe to assume. So by this, you can't assume that they are that it's always true, because there are exceptions like this problem, or many problems that involve the same thing like this. For this example, you are asked to find all the second order derivatives for the function. The important part to notice is that the mixed partial derivatives are equal to 2. This means that the Clair's theorem holds true if it isn't an exception in the piecewise function. For this problem, you need to solve for the quadratic Taylor polynomial, in which you first need to find all second order derivatives and then plug into the Taylor equation. To get your answer of qx comma y, the main idea being that you need to take from this is that the answer that you just got is what the problem would have been if you expanded it. Thus, you can see the relations of the original function and the end result. The function is differentiable at a point when there's a defined derivative at that point. What this means is that the slope of the tangent line of the points from the left is approaching the same values of the slope of the tangent of the points from the right. Like the second order partial derivatives, the differentiability is also given by these theorems. By these three theorems, sorry. These theorems state whether the points you are at or on. Let me repeat that. These theorems state that the points that you are on are able to be derived. The three theorems being, if f is differentiable at a comma b, then f is continuous at a comma b. If f of x and f of y exist and are continuous near a comma b, then f is differentiable at f comma b. And then Clair's theorem, if f is defined near a comma b and fxy and fyx exists and are continuous near a comma b, then fxy a comma b equals fyx a comma b. Let's take the function of the absolute value of x. This looks like it would be differentiable, which it is, but not at all the points, which, for example, is not differentiable at the point 0, 0, because there isn't a defined derivative at that point. Especially differentiability plays a large point in knowing if a point would have a hole or not, or whether if it's just, well, not differentiable at a point. Well, this problem is very basic, but it shows an underlying theme of differentiability. It asks to find the points in which it's not differentiable, in this case, it will be the points 0, 0. This problem asks numerous questions about the piecewise function. As you can see on the contour diagram, or from the contour diagram, 0, 0 is not shown, but in reality it is, because it is defined by the piecewise function. Likewise, it is differentiable at all points that aren't 0. It has partial derivatives, but it isn't differentiable at 0, 0. So what that means is that this is why there's an exception to the Clair's theorem, and it has issues with piecewise functions like this. Lastly, they are partial derivatives and they are continuous at 0, 0. So essentially, this is a very good problem and a really good reason for why there's not many exceptions, or there are exceptions to various things. For example, this was the only problems that was proven or shown in various chapters that always seem to break some of the rules. And this is why I added included into differentiability, because it plays a huge role in this too. And yeah, thank you for listening.